Next speaker is Ernst RASEL. Title is not yet provided, but I think it's about quantum technologies.
Yeah. First, I wish to thank Bremen for giving me the opportunity to be here. I feel really very much honored to be in this session, starting with definitely Carla's great presentation and awaiting the great and first results, Manuel Rodriguez. And for this, I really wish to express feeling that I feel very much honored. I'm happy to share my research, or our research, which is summarized in this artist picture, showing you here in warm Rome a picture of the frosty nights in Sweden at the Swedish Space Center and above, floating bees, seas, expanding freely. And actually, this is about the first space atom laser, which was revealed last year, more than a year ago now. And our motivation is, of course, that we want to exploit those for interferometry, matter wave interferometry, and I will report about perspectives for ground and in space. And I have to say, in a certain way, I really think if you would have asked me 10 years ago if these things are controllable and can be packed into sensors which will move into the field or even into space, I would have said, no, this is completely crazy. And many of the engineers also said it's completely crazy and your TRL level is too low, but we do our homework successively. And for this, I also want to thank my team effort. And I want to say that this actually started out with a couple of colleagues which are, oh, thank you, around here. On the very left are Hans-Jörg Dittus, and in the middle, Klaus Lemmerzahl, who started out with this business together with Wolfgang Erdmann on the right side. And actually, this picture was taken at the occasion of Klaus' 60th birthday, where we celebrated together with, of course, Carsten and Jürgen Müller, with whom we are cooperating for gravimetry based on quantum sensing. So yeah, I want to convey the message that actually atom matter wave interferometry is a paradigm change by exploiting both the Einstein condensates, and I will convey this message and motivate it with some simple introduction to matter wave interferometry, where you know that matter waves, matter has wave character. And if you ask about what is determining your wavelength, it's the velocity. Now, it's very simple to make the next step in saying, okay, what is then about coherence? And this means that actually you have to get extremely small wave velocity dispersion. And I want to convey that we now have the means to reach energy scales on the femtokelvin range, and in that sense really get extremely coherent matter wave sources, which give you both the accuracy and the resolution for improved measurements. And of course, we exploit and read out these wave features by performing interferometry, and we use as a beam splitter the absorption and simulated emission of photons. A photon itself, the kick is corresponding to an extremely small energy and velocity. Actually, just to give you a reference, more or less all laser cooling techniques are limited by or compared to the photon recoil limit, means the energy due to photon recoil, and we go far beyond that. And just to give you a feeling, what it means is if you absorb a photon recoil, you move depending on what the mass of your atom has from millimeters to centimeters per second. If you have extremely light atoms like lithium or helium. And I will show you that we now can succeed in transferring not only one or two photon recoils, but that BECs allows you to transfer thousands. And this is actually something what is requested for gravitational wave detectors. So this picture shows you an interferometer employing light pulses to split up both the Einstein condensate. And this picture shows you not only the unity gain, unity contrast you get with the interferometers, but also the enormous small velocity dispersion, because you can here clearly resolve the recall of a single photon limit. You see that the BEC is hardly expanding in this case with respect to the transferred photon. And this is how you can actually resolve those measurements clearly. And what is the motivation? Of course, I don't have to convey this message. I will not take the time. We want to exploit it to study gravity, and there's a variety of topics you are pretty much aware of. I just want to make aware of that the atom interferometry really brought into a discussion on about merging the ideas of classical tests like clocks and free fall experiments, because both are somehow interwoven in our devices, and also triggered a lot of publications on if actually gravity can cause classicality, and those things actually can be tested. And we think also that just from the precision you need, we are quite optimistic to improve on the most stringent tests today with atom interferometers. And an important part, of course, is for our research is also that we want to employ it for applications, for monitoring Earth gravity, and last but not least, our holy grail is to contribute to the detection of infrasound gravitational waves. And I will allude a little bit to it. Speaking about all this, this slide serves you to set the frame what you actually need for matter wave interferometry. And if you want to improve on the state of the art of today's gravity measurement, then you would like to go below 1 nanokelvin. So laser cooling is typically in the 100 nanokelvin to microkelvin regime. And this is mainly to improve accuracy. So you are not absolutely required to go far beyond, to extend the duration of interferometers far beyond what you can do today in the range of more or less a second that the atom interferometer has to span. Speaking about really going beyond what today you can test or restrict the equivalence principle, we speak already about timescales of 10 seconds, even 20, and we require 10 energies for the expansion of the atomic cloud to 100 picokelvin or even less. And when we speak about gravitational waves, where the time more or less is an important parameter determining the frequency of the gravitational wave you want to detect, you think about to extend this time from 10 to 20 to even 100 seconds. And there, especially on ground, you need energies, expansion energies, which are for this, what has been proposed so far, is even maybe making necessary to go below a picokelvin. So all these things there are no techniques known so far, have not been known so far, to reach even these energy scales. And when you talk about BECs, many people say this is something which is quite hard to estimate that you can do reliable measurements. And apart from this complexity, people also think about the low flux and the influence of the Milford energy. And I want just to report that more or less these, with atom chips, you can improve a lot of these parameters. Apart from that, you have a reliable and fast BEC generation, which is for measurements, of course, very important. And we can now achieve a decent flux in even transportable devices, so that we now build transportable gravimeters. We have there the opportunity of fast switching, and this is important for methods which I will present to you, like delta gig collimation. I will explain it. And actually, there can be much more features integrated necessary for interferometry. And last but not least, of course, they are compact and robust. They are used in the drop tower in Bremen and on a sounding rocket. So about the low flux, I want to refer you to a paper about employing multi-layer atom chips, where we have more or less atom chips being optimized for several phases of the experiment, starting out from laser cooling down to BEC, and which is compactified and actually was operated on the rocket in the drop tower and also will be in field gravimeters, giving you a flux of 10 to the 5 B atoms in a BEC per second, which is already, I think, the highest so far in the world still. And so this is actually a flux which people operate atom interferometers regularly when they really need to operate with cold atoms, because they have to do it by filtering with Raman cooling, but they can only filter it in one dimension. And the other is, of course, when you speak about BECs, people say this is a big problem is because atoms are so dense that more or less they see their interaction, the repulsion, and actually if you release it, then this repulsion will turn into kinetic energy, and so all what you gained being in the ground state of your atomic source is then wasted by expansion. But actually the important point here is the delta K collimation, that you have the point source character of the BEC, and this is similar like this picture shows you for a laser beam, that if you have a tight focus or a point source, then more or less a lens is acting to take out all the transverse momentum. And we do it in a way, but we do it on a sample which is standing or floating freely in space. Of course, has not the speed of light. And so we can do it in 3 dimensions by just more or less releasing the BEC in microgravity, letting it expand it so that the atoms get sorted according to the velocity, switching again on potential. For example, in our case, a magnetic potential, which was actually used for preparing the atoms, and in this way you collimate it. And I show you just why this is a game changer. I compare 3 methods: laser cooling, both Einstein condensates, and both Einstein condensates with delta K collimation, to show you what is the difference and why one is really a game changer, especially for. There was something which. Why does it not work? Let's see. Yeah. So it's a sequence of 4 seconds. And each shows you more or less how the atoms react in this simulations. And you see that in the case where you have BEC combined with delta K collimation, you have hardly a change. And of course, in space, you want to go to a macroscopic time scale, not only of 4 seconds, but 10 seconds and more. And that this is actually not only a simulation. I show you what we have been realizing in the last years, and which we are now even advancing to lower energy scales. Is here you see a gallery of BEC being delta K collimated, and you see how we even create a focus in this, and how well this is fitting with the simulations we perform. And so we have a quite good handle. And here actually we combine not only the lens, but also the more or less engineering of the collective excitations of the BEC. And all this is done in the drop tower, and not just in a standard experiment, because observing atoms over 2 seconds and longer is actually challenging in ground-based experiments. And we have to really study and convince us and others that we can handle all these methods and that we can bring these methods to life. We have now a variety of facilities in future, starting from more or less ground-based fountains on the very left side to rocket flights I will report in the second part on my talk on, and in future also in Hanover and in Bremen, an Einstein elevator for having a higher repetition rate than in the drop tower. But nevertheless, the drop tower is the only device which brings us really close to the timescale we want for what we want to perform in space, actually, for interferometer. But I speak a lot about employing it for space. I just want to point out that there's a lot of different new concepts which are just relying on data key collimated BECs, and I refer you to this list. And I just want a little bit to highlight double break interferometry, because due to the extreme low kinetic energy, expansion energy, we can very effectively employ what we call double break interferometry. I mean, if you know break interferometry or neutral interferometry, then in a nutshell, what we do is actually that we slide. You can slide two crystals, one in each other, and each of these crystals is taking care for one arm in the interferometer, scattering the BEC, as you see on the right side. And due to this, we can combine this with Bloch oscillations and have set a record, have now realized beam splitters with 1000 H per case, and the largest recoils in interferometers. And now you see the output after 200 H per K, and in the diagram up there you see that we see interference contrast at 400 H per K. And of course, we want to show you that we can perform the beam splitting. The papers on gravitational wave detection with atom interferometers show or demand to reach the sensitivity. And of course, we want to have there also at the end unity contrast, because we want to use entangled atoms together with those. This method, double break interferometry combined with Bloch oscillations, also gives you perspectives for new methods adapted to MEGA, for example, multi-loop configuration. As I said, you need, if you do just use standard interferometry tools, energies in the femtokelvin, but with multi-loop geometries, you can actually more or less work with what we have been achieving so far, and this gives you a big relief in rejection of noise, inertial noise on the Earth, such that we have been looking into these devices and compare. You see the red curve more or less in relation to what has been detected as a source for gravitational wave, and assuming also the efficiency of our beam splitters. So let's switch gears. In the last part of my talk, I want just to report about the implementation of a space atom laser, which was happened in January 23rd, 2017. Here you see the rocket just emerging from the launch pad, and in the red capsule is actually our both the isochrone apparatus. Here you see a picture of the team and the rocket engineers in the blue dresses. And with this, I really want to acknowledge this the great team effort, which was taken by all these PhD and postdocs, led by Stefan Seidel in the background. And this team has been is established by a large number of partners whom I all want to acknowledge with this slide. So it's amazing, but it worked out that we could make a full BEC apparatus, which was room filling maybe 50 years ago, into such a rocket, an atom chip apparatus. I show you with full featuring an interferometer, the laser systems and electronics. The electronics is built in our house with batteries as well as the atom chip apparatus. And here you see a close-up. More or less at the very heart is an atom chip, which is preparing a BEC and then has more or less all features that you can perform interferometry as we foresee, for example, for our gravimeters on ground. And you already see here that actually the atom chip is nowadays the smallest part of this device, and we are more or less limited by the classical things like vacuum technology, and so we will also work onto this. Here just some features that we have on ground, a BEC of 10 to the 5 atoms after 1.4 seconds, and for the experts, more or less, we could transfer them into the non-magnetic state, which we need for interferometry, and we could more or less employ traps for magnetic lensing and so on. So the remarkable is that this space flight only took 6 minutes, and so more or less this, we had to make a strategy between just let the experiment go, optimizing and reacting it, because you can imagine it's quite tough to react on a problem when the flight is over after 6 minutes. Nevertheless, we made 110 experiments, starting out with experiments on ground and during the launch phase of magneto-optical trapping, laser cooling and trapping, as, for example, required for atom interferometry and high vibrant environment. We had accelerations up to 12 to 17 G, and then more or less set in space beyond the command line, reset it, reinitialized the experiment, and then did studies on how our space atom laser is behaving. So I want to just to guide you through a few. The observation of the phase transition, of course, motivate our on-chip transport, and speak a little bit about interferometry. We are still looking into this. So here you see just a way how well our laser cooling worked while we had the launch. So the experiment was running all time, started before the launch and was continued. And the black curve shows you the boost phases with the switch on of the motors, and the blue dots the recapture mode. So you see it's actually robust as we expected, because we have been performing this already in the shaker table. So it's maybe one of the few experiments, BEC experiments running on a shaker table. And so I just want to briefly report on the observation of the phase transition. Here you see the typical bimodal distribution, where the broad distribution of the thermal ensemble is decreasing more and more with increasing temperature. And this is captured here by these two pictures, showing you on the one hand the thermal atoms, the red dots, the BEC blue dots, and the ratio both for space and on ground. And you know, sometimes you have even nice surprises in space. Instead of that it was working worse, it was actually working better than on ground. We attribute this that the gravitational sag has been more or less maybe being not fully optimized on ground to compensate for the sag, and so it was disappearing in space, and so we had a better loading of the thermal atoms, and also resulting in a higher atom number. You also see that we have not been going through full to and converting all atoms into a BEC, and this was, we had a shift in the magnetic field, what we found out when we studied this phase transition. So this was for us a very nice surprise, and also saying that you have to be very careful with the alignment, because what would happen if we would have had a worse signal. So in that sense, it shows that actually gravity has an impact. But of course, we could not test too many things in this direction. There would be, of course, a lot of room for optimizing loading and generation processes of BEC. The other important is that we, of course, want to transport and manipulate the BEC on the chip to release it. For example, we transported the chip, the BEC, from about 100 micrometer of the chip to about 1 millimeter, where we wanted to release it for further operations. And this is a delicate matter, because when you look into how the trap behaves, then of course this results in a decrease of the trap frequency, and you're getting quite susceptible to perturbations. And you also have to be very careful about the transport, because the transport is actually for us a tool to shape the collective excitations. On the other hand, if you just drive it too harsh, then you actually get a huge impact. And this is what we want to visualize here. So you can use the time of free evolution in space as a kind of a magnifying glass, where you actually look into the microscopic oscillation of the BEC onto the atom chip by just the shadow you detect much later when you let it expand it. And this oscillation is just due to the velocity, the vibrations on the atom chip you have to handle. And for us, it was a very big surprise that actually the theory is complying very well with our observations. You should maybe look into our first science about BEC in the drop tower, where we hardly could get in agreement any predictions of Schwader-Schlapnikov's model with our BEC. And here now, more or less, we have very good agreement with our models of the atom chip and the magnetic fields we can generate on. And actually, the only discrepancy was the excitation amplitude. And this resulted into a slight difference into the velocity. And this actually is coherent. Finally, you see the quite nice reproducibility of the setup that on all across all times, they more or less are expected to fall on a linear line, being undispersed released. So this is actually a very, very controllable source with adjustable velocity for both the ion condensates. And if you look into the dynamics, then without the theory, we would have probably guessed that we have noise. But what we see is actually the collective excitations we generate by the transport. And this is actually the continuous line, the line with respect to our few data points. And this makes us very optimistic that we actually can, because of the phase stability of this, that we can really do engineering with the help of the collective excitations. And of course, the motivation for this was to show that we can do interferometry. So we have been installing interferometer to more or less probe the coherence of the BEC and also performing Martinez type interferometer. This was a Bragg type interferometer, and this Bragg type interferometer actually had a speciality that it was modulated across the beam, so that what we actually have been happening is that you have in parallel many interferometers which you could more or less resolve just because we had a BEC with thermal atoms. You probably would have even had no contrast. And so the data analysis is going is now going with the theory models. You have to understand we have not a lot of data. So you would say, hey, why don't you publish them all immediately? Our paper is just now an archive of the first part of the results, but it is the theory which really gives us full access to what we can take out of all these data points. And this is why it actually takes a lot of effort to really understand and get out of this only 110 experiments. I mean, it's still what remarkable. We'll come to the Cold Atom Lab, which is now flying on the space station, and we would have happy doing 6 experiments with this. So you see about, and of course this is motivation why we want to go to the space station, very excited about CAL. So, I just more or less here summarize the Mayo's findings, that we are very optimistic to continue our rocket flight program, to go to the next steps, really performing a lens and extending the interferometry. And the second apparatus is actually operating with potassium. We have, I would say, one of the highest flux also for potassium. So we are very happy so far with the performance, and we'll combine it also with rubidium and perform some real interferometry, maybe the first interferometry in space for really over extended times. And this brings me to something what happened on very recently, because we are now in the middle of the future, that we have now cold atoms on the space station. Cold Atom Laboratory was launched May 21st. We are part of a team actually now having more time to explore our research together with Nicholas Bigelow. And this is, of course, about that we really want to show convincing that atom interferometry in space can be managed, of course, to a large part, triggered by the equivalence principle, and going maybe even beyond what we will learn today. This is our mission, and also contributing to infrasound gravitational wave detection on ground, and all this more or less will then lead to something like SD Quest. And I think this is the perfect transfer to Manuel Rodriguez's talk, who will speak about classical tests. Thank you for your attention.
Thank you very much, Ernst. Questions?
Thanks. First of all, I think your talk is very inspiring. I mean, it's very educational to understand what may be the current and perhaps tomorrow's prospects for probing very, moving bodies in very weak accelerations. So from a cosmological or astrophysical perspective, I mean, ideally, we would like to mimic and do a controlled experiment on a mini galaxy in the laboratory. So what does that mean? That means you're looking at small bodies, small mini Cavendish experiments, and very small accelerations. But at any rate, it will be more than one body. So what is the prospect of perhaps doing a free fall Cavendish type of experiment in your setup?
So, yeah, thank you very much. Of course, as I said, for the Grunge principle, we will work on a two-species setup of potassium and rubidium. But I think this is more about that we look how the Earth is attracting these two species and less a Cavendish experiment where a BEC is attracting another BEC. I think there you have to fear that the mass of the system is not big enough yet. On the other hand, there are a lot of people now, as you know, thinking about that they can take a microscopic body, bringing him into a superposition state, so that you have from this body emerging superposition of two gravitational fields being associated with these two locations. And indeed, I think that BECs are here a very good way of actually measuring the influence of this because you have extremely very well prepared sample of very well defined kinetic energy, very low expansion, and the possibility that you actually have extremely precise control of the external degrees of freedom because you can more or less just reflect what your laser manipulation gives you. The photon recoil is an extremely precise ruler also on recoil. So the transferred momentum can be very precise, and I think combining both is an interesting perspective, and I also propose this to people like Markus Aspelmeier and others for thinking into this direction, instead of having the complication of having two large bodies being in a superposition, just using one and looking into the impact, for example, on a BEC. Hope this replied to your question.
Okay, thank you. I'm Morg.
There were experiments in Grenoble with cold neutrons regarding the test of equivalence principle. Can you comment on this experiment, compare with your results?
So, if you talk about the latest experiments, this refers to a paper which I have been contributing together with Wolfgang Schleich on that actually the inertial and gravitational mass is appearing differently in the term when you have a bound system like in a trap. And I think this is a wonderful experiment. I think, but they aim for a complete different aspect, actually, a very interesting aspect, seeing that through energy, both the mass is appearing differently, and to verify and demonstrate those. But I think it is, for example, not competitive with something like what is microscope showing. And so these are really two very different aspects. I would not compare one with the others. We really think about to more or less achieve an accuracy in space like microscope or even better. So not sure if this, if you have in mind this experiments, which I very much admire, so I think it's very nice because it's very intriguing to see that in most cases when we deal with free-fall experiments, we assume the two masses drop out. But actually in the case when you look to the energy contributions, this is no longer true. They actually even range with a different power into the equation. And I think this is interesting aspect there.
I see no further questions, so then we thank you again, Ernst.
Thank you.